I'm currently a master's student at the University of Toronto in industrial engineering, and I started working at Vector as a applied ML intern this January. So I've been working on the a model-based reinforcement learning project with TELUS, and well, that's pretty much it. Okay, so yeah, good afternoon, everyone. Today, I'd like to present the main project I've been working on during my internship, namely the model-based reinforcement learning for energy-efficient HVAC control. For this presentation, I will begin by giving you an overview of the project, then break down the key algorithm used in the project, followed by the progress we made as well as the project deliverables. Finally, I will talk about the future work for the project. The model-based reinforcement learning for energy-efficient data center HVAC control project is a collaboration between Vector Institute and TELUS. Data center control, temperature control is a critical process for maintaining high quality of service. While maintaining temperature in an appropriate range is crucial, it is also important to note that every heating or cooling strategy has associated environmental and economic costs. For instance, a cooling strategy that uses unnecessary or excessive air conditioning will consume more energy than a strategy that better leverages free cooling. Free cooling is the process of cooling by exchanging heat with the lower temperature outdoor air, making it more cost and energy efficient cooling approach. As long as operational constraints are satisfied, opportunities to discover temperature control solutions that minimize energy consumption are highly valuable. In order to achieve energy efficiency for data center temperature control, TELUS proposed a novel dynamic programming approach for continuous state space model-based reinforcement learning problems called hyperspace neighbor penetration. Before diving into the hyperspace neighbor penetration algorithm, I'd like to briefly introduce continuous state space reinforcement learning problems. So in reinforcement learning, we try to train an agent to learn the best course of action, which we call a policy, for every possible state that the agent might be in. And in our problem, we want to control the temperature of the data center. So the agent should learn to change the HVAC system control based on the current room temperature. Now, since the temperature is a continuous variable, this means that we have a continuous state space reinforcement learning problem. If we were to control a discrete variable corresponding to a discrete state space, an agent would take an action to transition from one state to the next and receive a reward from the environment. And theoretically, an agent is able to experience every state and explore rewards on each of them. For our case, which is continuous state space, we will need a function approximation to represent the states. A classical approach for approximating continuous state space is tile coding. So in tile coding, we assume that the continuous state space is incremental. Then the locally linear transitions can effectively be discretized into relatively coarse ranges or bands of values as tiles. However, for slowly changing variables like the temperature, this approach can lead to situations where an action results in such a small change in the subsequent state observation that no discrete state transition has actually occurred. A naive solution could be to increase the granularity of this state space, but it would be computationally expensive or even impossible to establish an extremely granular grid system. We can get a better understanding by looking at figure 1 and 2 here. Firstly, the vertical x-axis on this is the state space of the continuous variable. We can see that this continuous variable has been segmented into several tiles from from V0 to V4. So we're turning into a continuous state space into a discrete state space, essentially. And in figure 1 on the left shows that when a variable changes quickly, the agent will take action A1 to transition from the tile labeled V0 to the tile labeled V4. This demonstrates that the classical method of tile coding works for fast changing variables as state changes enter tile after the agent takes an action. For figure 2 on the right, if we're working with a slowly changing variable like room temperature, the action taken by the agent does not move the agent from one tile to another. So it stays in the same tile, and as a result, the agent cannot learn the action value of different tiles properly. This means that the classical tile coding method cannot work for our problem, and as a result, TELUS proposed to use a method named hyperspace number penetration, or HMP for short. The idea of HMP is that, unlike the classical discretization method, the state value of each tile is not represented by a single value. Instead, HMP considers the whole range of the state values covered by the tile. Take tile 0 as an example. The tile covers the range from point B to point A. For state x0, action A1, point B transitions to point E, and point A transitions to point C. Although state x prime still lies in tile 0, its range of state values is now covered by both tile 0 and tile 1. The associate action value of A1, which is Q1, is now divided into Q1A and Q1B. And HMP uses both action values of Q1A and Q1B proportionally to update the tile value V0. For the data center HVAC control problem, temperature is a slowly changing variable that is incremental, and the transitions are locally linear. Hence, HMP would be an ideal solution for this problem. The goal for this project is to provide an open source reference solution for a model-based reinforcement learning agent using the HMP algorithm to control the HVAC system in a small room data center such that the energy utilization is minimized. Previously, TELUS had developed a functional prototype in the form of Jupyter notebooks, but they were unorganized and had little documentation. So we spent quite a bit of time analyzing and understanding the code. We then had several meetings with stakeholders from TELUS to discuss our understanding of the prototype, as well as some issues we noticed during our exploration. The prototype used a simulated environment of a small room data center in TELUS for training and testing the reinforcement learning agent, which contained confidential information from TELUS. In these meetings, we identified the data that cannot be open sourced and came to a conclusion that we should create 2 repositories as the project deliverables. A private repository for TELUS internal use, which includes the simulated environment so that they can apply the trained agent, and a public repository that hosts the open source reference solution for training the reinforcement learning agent. We abstracted and modularized the prototype to create the code base for the private repository and tested our code by comparing the trained agent's action values with the results provided by TELUS. From here, we removed all the confidential data and parameter values, as well as code that cannot be used in the absence of these values to create the open source repository, and added a detailed explanation for all methods and variables. In addition, the open source repository is also fully documented with solution overview and algorithm breakdown, which includes information about the state action space. The state space is constructed by the current temperature and the status of the HVAC system. The possible set of actions from a given state includes turning on a component of the HVAC system, such as the compressor, the heater, or the free cooling device, or letting the system idle. There are 3 different types of negative rewards associated with the temperature control environment. A power consumption reward that penalizes agent for consuming power, a device start reward associated with turning on the compressor or the free cooling device, and a temperature violation reward if the agent goes into a state that exceeds the allowed temperature range. The temperature change of each state action transition is determined by the state transition parameters. These parameters represent the rate of temperature change and are computed using linear regression from a time series temperature change dataset. Since the dataset is confidential to TELUS, the values for these parameters are removed from the repository. So unfortunately, I can't do a demonstration here. For the next steps, we plan to improve the generalizability and reproducibility of the open source reference solution. Now, limited by the confidentiality of the data and environment provided by TELUS, the reference solution doesn't have the state transition parameter values nor a simulated environment to apply the trained agent. Therefore, currently, we're working on adding the code for computing the state transition parameters so that anyone who's interested to use this method for their own environment can use this solution. We also plan on including an open source HVAC control dataset, as well as an open source HVAC energy consumption simulator for people to better showcase and demonstrate this reference solution. Thank you for listening.